We're going to do what in our book is considered section 21. We're going to talk about two different prep skills. The first one is classifying numbers into categories, and the second one is recognizing numbers in a given list. And so when we're classifying numbers into categories, we're basically deciding whether or not they fit into certain groups of numbers. So it says here that there's lots of categories of numbers: real numbers, imaginary, perfect squares, irrational, and so on. But for right now, we're going to just focus on whole numbers, integers, even numbers, and odd numbers. Whole numbers are of the type, they start with 0, they don't have any decimals or fractions in them, and they're only, after 0, they're only positive. So 0, 1, 2, 3. Integers is the whole numbers. You notice it has here 0, 1, 2, 3, but then it also has their opposites, so -1, -2, -3, and it would go on forever downward and upward, whereas the whole numbers only go forever upward. The even numbers is a subset or part of a set of the integers. It is anything that is divisible by 2. So 0 is kind of divisible by 2. I mean, 0 is divisible. 0 divided by anything is just 0. But then 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3. So anything that will divide by 2 evenly and give you back a whole number answer. And then the odds are the other integers that don't divide evenly by 2. So you have 0, 2, 4, and the ones that are the evens, and then the odds would be 1, 3, 5. So if we look at these, it says we want to classify each number as a whole number, an integer, an even, or an odd. And it could be in more than one category. So for instance, 100 is a whole number because it is in the 0, 1, 2, 3, 4, 5. You would eventually get to 100. It's also an integer because all whole numbers are integers. And it's also an even number because it's divisible by 2. So 100 is whole, an integer, and even. -27 is an integer, but it's not even because it's not divisible by 2, but it is odd. And it's not a whole number because it's negative. So -27 is only an integer and an odd. So now for these, I'm not going to go through all of these, but in your book there are answers to these. So if you look here, the answers for those 1 through 11 practice exercises are here in the back, and you can do those and check your answers. So now we're going to look at recognizing numbers in a given list. It says we just talked about deciding what categories a given number belongs to, and now we're going to take just a little different direction, and a list is going to be described to us. Then can we figure out if a specific number is in there? So it says let's consider the list that is 3, 6, 9, 12, and so on, following that pattern forever. Would 25 be on the list? What about 33? Well, this, if you look and try to discern what the pattern is, these numbers are all divisible by 3. So 3, add 6, or 3, you get 6, add 3, you get 9, add 3, you get 12. So these are all multiples of 3. So 25 would not be a multiple of 3, so it is not on this list. If I kept going, I would have 12, then 15, then 18, then 21, then 24, then 27. So if we kept going with this, we would not fall on 25. However, 33 would be, because if we went to 30 and then 33, that 33 is divisible by 3. It is a multiple of 3. The next thing that is described to us, or the next set that's described to us, is the even integers between 0 and 50. So is 50 an even integer between 0 and 50? And they say, we'll probably be tempted to say yes, but technically between means not including. So if they wanted to include those, they would say between 0 and 50 inclusive or including the endpoints or something like that. Since they didn't do that, they really mean 2, 4, 6, and then up to 48, but not including 50. So 50 is technically not in this set. And then here they describe it with the word inclusive. So it says, is 50 on a list of even integers between 0 and 50 inclusive? That means we are going to include 0 and 50. So we're going to go 0, 2, 4, 6, and we'd include all the numbers up to, all the even numbers up to 50. So 50 would be in that set because it would be at the end. And again, there's a set of practice exercises here, and you can go to the end of your of this section in our book. Let me tell you what number it is in our page number it is in our book. So in our book, if you want to check these answers, they are on page 310. Okay. So now we're on to section 22 in our book, and we're going to talk about our first objective is using the roster method. So the roster method is writing out a set of elements by writing them all out, usually, or by writing them all out and by putting set brackets around them. So in this example here, it says write the set of colors on a Rubik's Cube. So you may not know this, but the colors on a Rubik's Cube are blue, red, yellow, green, white, and orange. So in order to write that set of colors in the roster method, you'll notice that we say C equals. That's not necessarily always done, but we have to have these set brackets, and then we have to list everything out, and then another set bracket. So we would do set bracket, blue, red, yellow, green, white, and orange, and then we have to close up those set brackets. It doesn't matter what order these are in, though. You can write them in any order as long as you have all 6 colors listed. And then it says write the set of whole numbers less than 5 using the roster method. So it says less than, so that means we're not including. So they show here you're going to start with the first whole number is 0, and then 1, 2, 3, and 4. Close those set brackets. In order for it to be in the roster method, it has to have those set brackets. So there's a set of practice exercises, and as before, those are in the back. You could check those, try those, and check them. I would highly recommend you do that. Just pause the video, do the practice exercises, and then start the video back up. So now we're going to use set builder notation. When we're using set builder notation, it uses variables to represent different elements of the set. So we can use whatever symbol we want, but we can't use a number as long as it's not a numeral. So it says write this in set builder notation. So we're going to call these are vowels, A, E, I, O, U. So in order to put it in set builder notation, we're going to say it's the set of vowels, and I'm going to use the variable V like they did. And then we're going to put this little bar and then describe what we want. V is a vowel. So it's the set of all variable or all V's, all vowels, where the V's are a vowel, where V is a vowel. So you say what your variable is, and you can again use any symbol you want. Typically we just use a letter because it's easy, but then we put this bar every time, and then we describe what it is. So this, it says write the set 1, 2, 3, 4, 1, 2, 3, and then it stops and uses ellipses up to 10. So we're supposed to do all the numbers that are between 1 and 10 that are whole numbers. So in order to do that, again, you're going to choose a variable. They chose to use X. You could use any variable. You could use X, N, Y, Z, A, B. It doesn't matter. Where, in this case, X is a I'm going to do it a little different than they did, is a whole number less than or equal to 10. So they called it a natural number, which is a counting number. And then we want it to be less than or equal to 10. I guess when I do this, I should say n larger than 0. Because if I say whole number less than or equal to 10, that would include 0, and we don't want to do that. So I'm going to say whole number less than or equal to 10 and not 0. I just wanted to show you a different way to do it. We could also say x, where x is whole number, and then 1 is less than or equal to x is less than or equal to 10. So we could describe it different ways as long as you get those numbers and not any other numbers. So I called it a whole number between and including 1 and 10, or I called it a whole number less than or equal to 10 and not 0. They called it a natural number. Natural number is nice because it starts with 1, and then they said less than or equal to 10. This little symbol here you might not have seen before. That means element of. So x is an element of n. And that symbol n stands for natural numbers. Natural numbers are kind of alluded to here, but I'll say they're just like whole numbers except they don't include 0. So natural numbers is 1, 2, 3, 4. They're the numbers that you count with. They're also called counting numbers. You may have heard that. So go ahead and pause the video and see if you can do set builder notation for these, and then you can check on the answer sheet to see if you were correct. Section 23 in our book, we're going to look at interpreting a Venn diagram using set operations, the cardinality of a set, and the empirical probability. So a Venn diagram is a way to show all the elements of a set. So in a set, or in a Venn diagram, this one in particular, you have a circle that's listed as A. So this is the set of everything that's in A. This would contain everything that's in the set of B. And then anything that's in between them, or not in between, but in common with them, would go here. So if a number or an element or whatever we're talking about is in both set A and set B, we would put it here in the intersection of the two. Anything that's not in A or B, but it's in what's called our universal set, we would put on the outside. So let's look at one. It's a little easier to see it with some numbers in it. So for instance, 1, 9, 12, and 3 are in our universal set, but they're not in A or B. These numbers are all in A. 8, 15, 10, 45, and 59 are all in A, but 10 and 45 are also in B. So if we listed B, we'd say 24, 10, 45, 32, and 18. So all 5 of those numbers are in B, but 10 and 45 are also in A. So A and B share those two elements. If you want something that's not one of the sets, you can mark it with a little tick mark. So they do that down here. Just a second, we'll do it. So set A consists of everything that's in the circle A. So as we said before, that would be 8, 15, 59, 10, and 45. So if you wanted to list out the set A in the roster method, A is equal to the set of 8, 15, 59, 10, and 45. Then we'll do the same thing with B. I'm going to write it up here since we can't really get both of them on the same page. So B would be equal to 10, 45, because even though they're in A, they're still in the circle of B. B is everything that's in the circle. So 10, 45, 24, 32, and 18. And then if we wanted to list what's not in B is anything that's outside that circle. So it doesn't say it can't be in B or A, it just says it can't be in B. So B with a little tick mark means everything that's not in B. So 8 is not in B, 15 is not in B. 59 is not in B. I can't list 10 and 45 because even though they're in A, they are in B also. 12, 9, 1, and 3 then are outside of either of those circles. And so they would also be not in B. So 8, 15, and 59, the three that are in A that are not in B, and then 12, 9, 1, and 3, the ones that are outside of A and B altogether. Here's a set of practice problems that you could work on. So I would pause the video and do those, see if you're understanding them, and then go to the back here and look at your, or not the back, but the later page here, and see if you have your answers correct. So our next thing that we're going to do for an objective is use set operations. So we're going to look at intersection, union, and then difference. So an intersection of two sets is the set of all elements that are in both A and B. So when we were talking up above, it'd be where the two circles overlap each other. This would be the intersection. Okay, anything that's in B and A. The union is anything that's in one or the other. So if it's in A, you list it. If it's in B, you list it. If it's in both, you list it. The difference between two sets is where you take everything that's in A but not in set B. So let's practice this. So it says first we're going to find A union B, and we're going back up to this Venn diagram, which is kind of a pain. Alright, so we're going to go back up to this Venn diagram, and they want us to do the union of A and B, I believe is what we were going to do first. Yes, the union. So the union of A and B, I'll put it up here. So A union B would be equal to anything that's in either set. So I'm going to list 8, I'm going to list 15, I'm going to list 59, I'm also going to list 10 and 45, and I'm going to list 24, 32, and 18. A union is anything that's in one or the other or both. Next, I believe it asks for an intersection, and double check. Oh, no, they don't. They ask for B minus A. So we'll do that. So B minus A would be anything that is in B and then take out anything that is also in A. So B minus A would be anything that's in B. So that would be 24, 32, 18, 10, and 45, but then it says subtract out anything that's also in A. So we're going to not include, we're going to subtract out 10 and 45 because we don't want to include anything that's in A. And then the last one that they have for this is they want us to do A not intersect B. When they get a little complicated like this, the best thing I can recommend is to do them separately and then do whatever they want for a operator. So A not intersect B. The first thing I'm going to do is I'm going to write down what A not is. So A not is anything that's outside of A. So 12, 9, 1, and 3 aren't in A or B. I can't include 8, 15, 59, 10, or 45 because those are all in A. I want just A not. So I'm going to leave those out and I'm going to do 24, 32, and 18. So that's A not, and then we want to intersect that with what's in B. So B is 10 and 45 and 24 and 32 and 18. And the intersection is anything that they share in common. So is 10 in both sets? No, it's not. Is 45 in both sets? No, it's not. 24 is, though. 24 is in both sets. 32 is in both sets. And 18 is in both sets. So not in A intersected with what's in B is only 24, 32, and 18. So anything that is not in A, but it is in B. And that actually ends up being the same answer that we had up here for B minus A. So there's some practice problems. I would pause the video right now and answer these 3 questions, 4, 5, and 6, and then turn it back on and we'll talk about cardinality of a set. Okay, so our third objective here is to find the cardinality of a set. A cardinality of a set, which is just n of A, this n means number in, and it's just the number of elements that are in a set. So n of B means just how many things are in B. So we had already talked about what the set B had in it. It had 10, 45, 24, 32, and 18. So n of B would be 5 because it's just how many things it has in it. So 1, 2, 3, 4, 5 things in B. Not in B, again we'd already kind of talked about, not in B is 12, 9, 1, 3, 8, 15, and 59. And so n of B not would be 7 because there's 7 things in the numbers that were listed above in that universal set that were not in B. So again, here's a set of practice problems you can try. I'd go ahead and pause the video, try these problems, check your answers, and then turn it back on for computing an empirical probability. So now for our probabilities. An empirical probability is based on the observed cardinalities of a set. So what does that mean? So it says if you choose an element at random from the universal set shown in objective 1, find the probability that the element is in set B. So they want to know if you draw any random number from above, all the way back up here. So from this original set here, what's the probability that if you draw a number, it'll be from B? Well, we have to know how many are in the universal set, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's what's in the universal set. That's all the numbers that are within the box. But there's only 5 that are B. So we have a 5 in 12 chance that we would get an element of B if we picked out of that set of all the numbers. So 5 out of the 12 numbers. Now it says if you choose an element at random from the universal set, find the probability that the element chosen is in the set A intersect B. Well, up above we knew that A intersect B was just 10 and 45. Those were the 2 numbers that were in both. And again, the bottom number is just going to be the whole universal set, every number that we had. So out of this, there were 2 that were in A and B out of the 12 total numbers. And then we really should reduce that probability to 1 in 6. And again, we have a set of practice exercises that you can work on and then check in the back. So now we're working on section 24 from our book, and we're filling in a Venn diagram and interpreting a shaded portion of a Venn diagram. By the way, this term Venn comes from the person who invented it. Their last name, I believe, was Venn. If it's not Venn, it was part of their name. So from a universal set with 100 elements, there's 20 elements that are in both sets, 32 in set A and 45 in B. So we've got 20 that are in both, 32, I'm going to write this over here, 32 that are in A, and 45 that are in B. Now that doesn't mean we just want to slap those into each of the categories. The 20 elements in set A and B is important. We're going to put that in the center here. So in region 2, there's going to be 20 elements. But it says there's 32 elements in set A. It doesn't say there's 32 additional elements. It says there's 32 total. But we've already accounted for 20 here. So 32 minus the 20 that we already put in the shared portion here leaves 12 on the outside. And then here it says we have 45 elements in set B. Same thing. That means between this region and this region total we want to have 45. So we've already listed 20, so 45 minus 20 leaves us 25 elements for here. So now if we look back at this, we do have 20 elements that are in both sets. We have 32 elements in set A because we have 12 and 20, that's 32. And then we have 45 elements that are in set B. 20 and 25 makes 45. And so here's 3 practice problems you can do. I think I'm going to do this first one actually because there's one thing that they didn't really cover very well in this example, and that is the fact that there could be, does it say up here? It doesn't. So now I want to try one where it has extra elements that aren't in A or B. So here it says there's 342 elements in the universal set. That means when we're done, this box has to have 342 total in it. So we'll start with that there's 96 elements in A and B. So that would be 96 here. Then it says there's 102 elements in set A, but remember we've already accounted for 96. So 102 minus 96 is 6. So there's 6 elements in A that are not in this intersection part here. And then there's 51 elements that are neither in A or B. So we don't put them in either, we put them on the outside here. So now, how many are in B? There's going to be some elements in B, but we don't know how many until we do a little arithmetic here. So we have to go back where it says that there was 342 elements altogether. Well, we've accounted for 6 that are in A, but not in the intersection. We've accounted for 96 that are in the intersection, and we've accounted for 51 that are outside. If I add those together, that gives me 102, 153 if I've added correctly. But I need 342 elements total. So 342 minus the 153 gives me, you don't have to do this by hand, I just don't want to dig my calculator out. So that leaves us 189 elements that are in B. So in other words, I would want the 189 that I have in B that aren't in the intersection, plus 96 that are in the intersection, plus 6, plus the 51, that should total 342. I'm going to double check. 15, 21, 22, so far so good. 10, 19, 24, and yes, that adds up to 342. So that's how you do that. You just kind of go by the process of elimination until you have everything taken care of. And that's it. So go ahead and do these other few practice problems here. Check your answers on page, what did I say? They're up on pages 310 and 311 in our course book. And when you get done with that, if you feel like you're understanding those okay, you should be ready for the homework. And this is the only video for this week. So there's not a second video. These 4 short sections for notes is all you need to turn in.